Hello and welcome to Math World, the world where difficult math can be a very easy one. So today, dear friends, we are going to speak about geometric sequences, and we are going to solve the top 5 hardest exercises in geometric sequences that were presented in different exam papers. So let's start with exercise number 1. If the sum of the expression 2 to power n plus 1 when n goes from 1 to x is equal to 4092, find the value of x. So the idea for the first exercise is to analyze a little bit our sum. So we have the sum of the expression 2 to power n plus 1 when n goes from 1 to x. Let's expand a little bit this sum. So for n equal to 1, we will get 2 to power 2 plus for n equal to 2, we will get 2 to power 3 plus for n equal to 3, we will get 2 to power 4 plus and so on till 2 to power x plus 1. And from our condition we have that this sum is equal to 4092. If we analyze attentively the left hand side of our equation, we can see that in fact we had the sum of the geometric sequence. So here is the sum of the geometric sequence where the first term u sub 1 is equal to 2 to power 2, which is equal to 4, and the common ratio, let's denote it by r, is equal to 2. So what do we have to solve? This means that we have to solve the equation the sum sub x equals to 4092, where x means the number of terms in our geometric sequence. As we know, the formula for the sum of the first x terms of the geometric sequence is equal to u sub 1, the first term of the geometric sequence, times r to power x minus 1 over r minus 1, where r is the common ratio. So in our case, s sub x would be equal to 4 times 2 to power x minus 1 over 2 minus 1, or 4 times 2 to power x minus 1. So we have to solve the equation 4 times 2 to power x minus 1 is equal to 4092. If we divide both sides by 4, we will get 2 to power x minus 1 is equal to 1023. 2 to power x is equal to 1024. Because 1024 is equal to 2 to power 10, we will get that x is equal to 10. So the answer to our question is x is equal to 10. Let's move to exercise number 2. In exercise number 2, we have the following information: that a, b, and c are consecutive terms of both an arithmetic and geometric sequence, and we have to prove that in this case a is equal to b and is equal to c. So what do we have? We have two sequences. We have an arithmetic sequence and we have a geometric sequence. So we have that for the arithmetic sequence, a, b, and c are consecutive terms, and for the geometric sequence, the same a, b, and c are also consecutive terms. So if a, b, and c are consecutive terms of an arithmetic sequence, this means that the difference of any two consecutive terms is a constant. So this means that b minus a is equal to c minus b, or a minus b is equal to b minus c, or 2b is equal to a plus c. Because a, b, and c are consecutive terms of the geometric sequence, this means that the ratio of two consecutive terms is a constant. This means that b over a is equal to c over the b, or a over b is equal to b over c, or b squared is equal to a times c. So, using this information, we have to prove that a is equal to b and is equal to c. I will work out with 2b is equal to a plus c, and b squared is equal to ac, and we will prove that a is equal to b and is equal to c. From 2b equals to a plus c, we had that b is equal to a plus c over 2. And if we substitute in this relation b with a plus c over 2, we will get that a plus c over 2 square is equal to ac, which is equivalent to a square plus c square plus 2ac over 4 is equal to ac. Multiplying both sides by 4, we will get that a square plus c square plus 2ac is equal to 4ac, or a square plus c square minus 2ac is equal to 0. But a square plus c square minus 2ac in fact is a minus c square. So a minus c square equal to 0. This implies the only case that a minus c is equal to 0, which is equivalent to a is equal to c. So we proved that a is equal to c. Now, going back, that b is equal to a plus c over 2, and having that a is equal to c, we have that b is equal to a plus a. Instead of c, we can put the value a, because a is equal to c, so we will have that b is equal to a plus a over 2, which is 2a over 2, which is a. So we have that b is equal to a. So because a is equal to c and b is equal to a, we prove that a is equal to b and is equal to c. And this is the solution for the second exercise. Let's move to exercise number 3. In exercise number 3, we had the following: that x, y, and z are consecutive terms of a geometric sequence. If 3 times x plus y plus z is equal to 7, and 9 times x squared plus y squared plus z squared is equal to 91, we have to find the values of x, y, and z. So, what do we have here? We have that x, y, and z are consecutive terms of a geometric sequence. So, these three terms are consecutive terms for a geometric sequence. This means that the ratio of two consecutive terms is constant. So, from this we can write that y squared is equal to x times z. So we have a very important information. Now what do we have more? We have that 3 times x plus y plus z is equal to 7. Or it implies that x plus y plus z is equal to 7 over 3. Next we had that 9 times x squared plus y squared plus z squared is equal to 91, which implies that x squared plus y squared plus z squared is equal to 91 over the 9. So for finding x, y, and z, we have to solve the simultaneous equations y squared is equal to xz, x plus y plus z is equal to 7 over 3, and x squared plus y squared plus z squared is equal to 91 over 9. So, how we are going to proceed? We are going to raise to power 2 the both sides of the relation x plus y plus z is equal to 7 over 3. So from this one we will get that x plus y plus z raised to power 2 is equal to 7 over 3 raised to power 2, or equivalent to the fact that x squared plus y squared plus z squared plus 2 times x times y plus x times z plus y times z is equal to 49 over 9. Next, because x squared plus y squared plus z squared is equal to 91 over 9, we can replace in this relation x squared plus y squared plus z squared with 91 over 9. So we will get the following equation: 91 over 9 plus 2 times yz plus xz plus yz is equal to 49 over 9, or 2 times xy plus xz plus yz is equal to minus 42 over 9, or xy plus xz plus yz, if we divide both sides by 2, we'll get that this is equal to minus 21 over 9, which in fact is minus 7 over 3. Next, we see that we had that y squared is equal to x times z. So in this last equation, instead of x times z, we can substitute it with y squared, and our last equation will take the form xy plus y squared plus yz is equal to minus 7 over 3. Next, we can take the common factor y from the left side of our equation, and we will factorize it in the form y times x plus y plus z is equal to minus 7 over 3. And next, we are going to use the fact that x plus y plus z is equal to 7 over 3. So substituting this in the last equation, we will get that y times 7 over 3 is equal to minus 7 over 3, from which we get that y is equal to minus 1, and we found the value for y. Going back to our simultaneous equations, we'll have that x times z being equal to y squared, and now y being equal to minus 1, it will be equal to 1, and x plus z plus y substituting by minus 1, so minus 1, is equal to 7 over 3, or x plus z is equal to 7 over 3 plus 1, or x plus z is equal to 10 over 3, from which we can write that z is equal to 10 over 3 minus x. And now, if we substitute z with 10 over 3 minus x in this equation, we will get that we can find x from the following equation: x times 10 over 3 minus x is equal to 1, minus x squared plus 10 over 3x minus 1 is equal to 0. Multiplying both sides by 3, we'll get minus 3x squared plus 10x minus 3 is equal to 0. So we obtain the second order equation in the variable x. So solving it with the formula, we will get that either x is 0 to 3 or x is 0 to 1 over 3. For x is being equal to 3, we will get that z is equal to 1 over 3, and for x being equal to 1 over 3, we'll get that z is equal to 3. So the answer to our question is the following. We have x equal to 3, y equal to minus 1, and z equal to 1 over 3. So we have this geometric sequence with the common ratio being equal to minus 1 over 3, or one answer. On the second answer, x equal to 1 over 3, y equal to minus 1, and z being equal to 3. So we have another geometric sequence with the common ratio being equal to minus 3. And this was the third exercise. Let's move to exercise number 4. So, exercise number 4 tells us the following. Suppose an arithmetic sequence and a geometric sequence with common ratio r had the same first two terms. Show that the third term of the geometric sequence is this times the third term of the arithmetic sequence. So what do we have in this exercise? We have an arithmetic sequence and we have a geometric sequence. We also know that our geometric sequence has the common ratio. So the common ratio is r. Also, we had the information that the first two terms of our geometric sequence are also the first two terms of the arithmetic sequence. So this means that if u sub 1, let's denote it by a, is the first term of our geometric sequence, u sub 2 in this case will be ar, because r is the common ratio. This implies that let's denote it by m sub 1. The first term of our arithmetic sequence will also be a, and m sub 2, the second term of the arithmetic sequence, will be ar. We have to prove that the third term from the geometric sequence divided to the third term of our arithmetic sequence will give us this answer. So let's deduce the third term of the geometric sequence. Because the common ratio is r, the third term will be ar squared. Let's now deduce the third term of our arithmetic sequence. For this, we have to find the common difference. So the common difference d will be equal to the second term minus the first term. So in our case, it's ar minus a. So the common difference for our arithmetic sequence is ar minus a, And in this case, the third term will be the second plus the common difference, and it will give us 2ar minus a. Now we have to prove that if we divide the third term of the geometric sequence to the third term to our arithmetic sequence, we will get the value r squared, or the 2r minus 1. And let's prove it. We have that the third term of our geometric sequence is ar squared, and the third term of our arithmetic sequence is 2ar minus a. So we will get that it is ar squared over, if we take the common factor a, we will get a times 2r minus 1. And simplifying a and a, we will get the answer r squared over 2r minus 1. The thing that we had to prove. So, in this way, we solved exercise number 4. Let's move to exercise number 5. In exercise number 5, we have the following. The first, the fifth, and the 17th term of an arithmetic sequence are the first three terms of a geometric sequence. The sum of the first four terms of the arithmetic sequence is 28. Find the common difference of the arithmetic sequence and the common ratio of the geometric sequence. So what do we have in this exercise? We have an arithmetic sequence, and we have also a geometric sequence. What do we know about these sequences? We know that the first term, let's denote it by u sub 1, the fifth term u sub 5, and the 17th term of the arithmetic sequence u sub 17 are the first three terms of the geometric sequence. So if the first term of the geometric sequence we denote it by m1, it will be equal to u sub 1. The second term denoted by m sub 2 will be equal to u sub 5, and the third, m sub 3, will be equal to u sub 17. What do we also know? We know that the sum of the first four terms of the arithmetic sequence, so u sub 1 plus u sub 2 plus u sub 3 plus u sub 4 is equal to 28. And we have to find the common difference and the common ratio of these sequences. So, let's denote the first term of the arithmetic sequence to be equal to x. And let d be the common difference. So, because d is the common difference and x is the first term, this means that u sub 5, the fifth term, being equal to the first terms plus 4 times the common difference, it will give us x plus 4d. Next, the 17th term, being equal to the first plus 16 times d, it will be equal to x plus 16d. So, this means that the first term of our geometric sequence is x, the second term is x plus 4d, and the third term is x plus 16d. And because we have three consecutive terms of the geometric sequence, this means that the ratio of any two consecutive terms is constant. So this means that x plus 4d over x is equal to x plus 16d over x plus 4d. Next, multiplying this equality by x times x plus 4d, we will get that x plus 4d squared is equal to x times x plus 16d. So if we expand the left side, we'll get x squared plus 16d squared plus x plus 8xd is equal to x squared plus 16xd, or 16d squared minus 8xd is equal to 0. So if we factorize the left side, we'll get 8d, a common factor, times 2d minus x is equal to 0. So this implies that either d is equal to 0 or 2d minus x is equal to 0. So x is equal to 2d. So we have two situations. So case number 1. If d is equal to 0, this means that we have a constant arithmetic sequence. So our arithmetic sequence is a constant sequence. So this means that u sub 1 is equal to x, u sub 2 is equal to x, u sub 3 is equal to x, u sub 4 is equal to x, and so on. So this means that the common difference is 0, and our geometric sequence has the first term being equal to x, the second being equal to x, and the third being also equal to x. This means that the common ratio is equal to 1. Now, the case 2. If d is different from 0, we have that in this case, from this equality, x is equal to 2d. Now, for finding the common difference, we will use the information that the sum of the first 4 terms of our arithmetic sequence is equal to 28. So, this implies that x plus d plus x plus 2d plus x plus 3d is equal to 28, or 4x plus 6d is equal to 28. And because x is equal to 2d, substituting x with 2d, we will get the following, that 8d plus 6d is equal to 28. 14d is equal to 28, so d is equal to 2. D being equal to 2, x is equal to 2d means x is equal to 4. So we have that our arithmetic sequence has the common difference d equal to 2. Now it remains us to find the common ratio of our geometric sequence. For this we know that our first term m1 is equal to x, so is equal to 4, m2 is equal to x plus 4d, so it will be equal to 4 plus 4 times 2, this means equal to 12. So the ratio will be the second term divided to the first term, so it will give us 3. So the answer to this question is the following. We have two cases. Case number 1, the common difference is equal to 0 and the common ratio is equal to 1, or the common difference is equal to 2 and the common ratio is equal to 3. So this was the last exercise from our presentation. At this point, dear friends, I want to thank you very much for your attention, and as always, please like this video, share this video with your friends, And please don't forget to subscribe to our channel to find new presentations about top 5 hardest exercises from different exam papers in different teams. Thank you very much and good luck to you.